In the beginning, there was silence, not the kind we know on Earth, where a lack of sound is a pause between moments, but the true silence of the universe. But before we continue, please make sure to subscribe and leave like for more sleepy science videos. It is not empty here. It is simply vast, so vast that the distances between the wandering particles of hydrogen and helium seem immeasurable. This is the quiet of deep time, the hush that has existed for billions of years before we, as thinking creatures, learned to name it. Somewhere in this grand expanse, hidden in the veils of a cold molecular cloud, something subtle begins to happen. It does not roar to life with sudden drama. It starts with a slow gathering, a gentle tugging as gravity, the quiet architect of the cosmos, draws invisible threads together. It is here, among these drifting fragments of cosmic dust, that we will meet Aurelia. She is not yet a star, not yet the brilliant furnace she will become, but already her story has begun, and with it, a question stirs in our minds. How can something so bright, so seemingly eternal, have an age at all? From the vantage of the human mind, stars feel immortal. We gaze upon them on cold winter nights, and they do not seem to change. Generations pass, empires rise and fall, continents shift beneath our feet, and still those same constellations mark the sky as they did for our distant ancestors. Some of the light we see tonight left its source before humans even existed, before mammals roamed the earth, before our planet's continents had settled into their present shapes. This illusion of permanence has inspired poets to write of stars as eternal witnesses, cosmic sentinels that watch unblinking across the ages. And yet, science whispers a more complex truth. Like all things born in this universe, a star has a beginning, a middle, and an end. Even Aurelia, though she will outlive every tree, mountain, and ocean on our planet, cannot escape the slow ticking of the cosmic clock. The irony lies in perspective. To a mayfly, whose lifespan may be measured in hours, a single human being might seem eternal. To us, a star's life, measured in millions or billions of years, feels as close to infinity as we can imagine. But to the universe itself, 13.5 billion years old and counting, the life of a star is just another chapter, long by our standards, but still finite. It is within this framework that astronomers speak of a star's age, not in terms of when it first shone in our sky, but when its nuclear heart first began to beat. For Aurelia, her age will not be counted from this quiet prelude, but from the moment her core ignites and the fusion of hydrogen into helium begins. Here, in the shadowed folds of the nebula, that moment still lies in the future. For now, she is an embryo of sorts, a loose cloud of matter being drawn inward, her atoms colliding more frequently as the gravitational net tightens. This is not a process that can be rushed. The universe is patient. Over hundreds of thousands of years, the core will grow denser, hotter, until the pressure reaches a tipping point. When that threshold is crossed, fusion will ignite, a process that will release more energy than anything we can fathom, energy that will push back against gravity's relentless pull and stabilize her form. It is the moment that will transform Aurelia from an anonymous knot of gas into a star. But for now, we are in the hush before the first breath. And so the question deepens. If she will live for millions, perhaps billions, of years, if her light will cross unimaginable distances to shine on worlds she will never know, what does it mean to say that she will age? In our world, age brings change we can see. A tree grows taller, a person's face lines with time, the seasons turn. But for a star, change is slow, subtle, hidden within the fiery depths. Astronomers track these changes with the precision of watchmakers, reading the fingerprints of starlight to discern its temperature, composition, and stage of life. They measure the hydrogen content of the core, the rate of fusion, the balance between gravity and radiation, all to determine where on the grand stellar timeline a given star resides. By this measure, Aurelia will someday be called young, middle-aged, and old, even if to our naked eyes she seems unchanged. The truth is that stars are not truly eternal even in the grandest scales. Given enough time, every one of them will exhaust the fuel that keeps them shining. Some will fade gently into cold embers. Others will end in cataclysmic detonations, scattering their substance back into the interstellar sea. Aurelia's fate will be determined by the mass she carries at birth, for in the world of stars, size is destiny. If she is small, she will burn her fuel slowly, lingering for eons. If she is large, she will blaze with such intensity that her lifetime will be brief by stellar standards, though still thousands or millions of times longer than a human life. In this way, even the stars obey the same truth that shapes all things. Beginnings lead to endings, no matter how far apart they seem. As we drift with her in this vast nebula, we might reflect on the poetic contradiction at the heart of her existence. She is forming from the ashes of older stars, atoms forged in the hearts of suns long gone. Their own lives ended in supernovae or in the gentle dispersal of planetary nebulae. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were made in the furnaces of ancient stars and scattered into space. Aurelia's own life will someday add to that cycle, her matter becoming part of new clouds, new worlds, perhaps new life. In this way, even the concept of end becomes blurred. A star may die, but its substance lives on, reshaped, reborn, reimagined by the universe. And so, our question, how can a star have an age, is really two questions. The first is physical. We can measure the processes that mark the passage of stellar time. The second is philosophical. Why do we, whose own lives are so fleeting, care about the lifespans of things that will never know us? The answer may lie in our own longing for permanence, our desire to find something in the universe that stands beyond decay. Stars, for all their grandeur, remind us that even the mightiest are bound by time, and that there is a strange beauty in impermanence. It is not their endlessness that makes them remarkable, but their ability to burn so brightly for as long as they can. Aurelia's light has not yet touched the cosmos, but already she is part of a story older than galaxies. We will follow her from this first moment of gathering to the day her last atoms drift away into space. Along the way, we will see that her age is not a flaw in her eternity, but the measure of her journey. The stars we see in the night sky are not frozen in time. They are living things, each at a different point in their own arc of existence. To understand them is to understand that even in the vast silence of the cosmos, time moves forward, and every light we see is telling a story that began long before we arrived to listen. In the shadowed reaches of a spiral arm of the galaxy, far from the crowded stellar neighborhoods where mature suns blaze in their glory, lies a vast and silent expanse of cold. It is not the cold of a winter's night on Earth, where air bites at the skin and frost creeps across glass, but a deeper, more absolute chill, the kind that hovers just a few degrees above the universe's ultimate zero. This is a molecular cloud, an interstellar womb of gas and dust so tenuous that a cubic meter may hold fewer atoms than a breath of air on the highest mountain. To human eyes it would be almost invisible, a dim smudge blotting out the background stars, but in truth it is dense compared to the emptiness around it. And in the world of space, density is destiny. Here, in this murky veil, the first whisper of Aurelia's existence stirs. It begins almost imperceptibly, with a ripple, a subtle imbalance in the cloud structure, perhaps the faint shockwave from a nearby supernova, perhaps the tidal tug of passing stars, perhaps only the random currents of gas drifting in the cosmic wind. Whatever its cause, this ripple disturbs the evenness of the cloud, and in one small pocket, hydrogen and helium atoms find themselves drawn closer together. The force at work is gravity, patient and relentless. It does not announce itself with violence, but with a slow, steady insistence, pulling at every particle, coaxing them into a tighter embrace. Over vast stretches of time, this tiny knot in the cloud becomes ever so slightly denser than its surroundings, and with greater density comes greater gravitational pull, which draws in more matter still. A feedback loop has begun, and in its quiet spiral, Aurelia is conceived. The region in which she forms is far from static. Dust grains, microscopic shards of silicates, carbon, and frozen water drift in the dimness, colliding gently, sticking together under electrostatic charges, forming clumps that will one day be swallowed into the growing heart of the protostar to be. This dust dims and scatters light from outside, creating dark lanes visible against the richer star fields of the galaxy, a kind of cosmic privacy curtain around her earliest days. If we could stand in the cloud and watch, we would see almost nothing, perhaps the faintest glow from molecules excited by nearby ultraviolet light. But in wavelengths invisible to the human eye, infrared, millimeter, and radio, the cloud comes alive. A glowing map of density and temperature, its cold knots like seeds waiting to sprout. Inside Aurelia's seed cloud, collisions between atoms grow more frequent, raising the temperature by the smallest degrees. At first, this change is barely measurable, but in time it will matter. The delicate balance that has held the cloud in a slow drift for millions of years is tipping. Gravity is winning. Gas that once wandered freely is now bound, moving inwards along invisible lines of force toward a common center. The scale of it is staggering. What will one day become Aurelia is already larger than the orbit of our solar system, yet it is shrinking ever so gradually into something compact and hot. Around her forming heart, the cloud is anything but uniform. Fingers and filaments of gas snake inward, feeding her growth. Some may fragment, giving rise to sibling stars that will share her nursery. Others may remain diffuse, to be swept up later or to drift away into the galactic current. For now, the most important story is happening deep inside the forming core. Here, the increase in density amplifies gravity's pull. The inward fall of matter converts potential energy into heat, raising the core temperature degree by degree. It is still far from the millions of degrees required for nuclear fusion, but the path is clear, and there is no turning back. Though we might imagine the birth of a star as a moment of fiery explosion, the truth is slower and more graceful. The cloud contracts over hundreds of thousands of years, almost lazily by our standards, yet with a sure purpose. The gas spirals inward, conserving its angular momentum, and as it does so, the whole structure begins to spin faster, like a skater pulling in their arms. This rotation flattens the infalling material into a disk around the central mass. From this disk, in the distant future, planets may form, small echoes of Aurelia's birth, each with their own stories. But right now, the disk's role is to feed the growing protostar at its center, funneling matter inward through tangled streams of magnetized plasma. Aurelia's earliest light is not the visible radiance of a star, but the faint warmth of compression, radiating away in infrared. In the hidden language of the universe, this glow says, something is happening here, something inevitable. The pressure in her core continues to mount, and with it, the temperature. The atoms at the center are crowded so closely now that their motions are constrained, collisions constant, the heat trapped by the opacity of the surrounding gas. Every particle that falls inward increases the gravitational squeeze, which in turn raises the temperature further, in a cascade that will culminate in a transformation as profound as the ignition of life itself. Around her, the larger molecular cloud continues to drift, reshaped by the slow churning of stellar births and deaths. Somewhere nearby, Other ripples are gathering into their own knots. Other stars beginning lives that will run parallel to hers. Some will be brighter, more massive, burning their fuel in dazzling bursts that end in supernovae. Others will be dim red dwarfs, their lives stretching for trillions of years. Aurelia does not yet know her place among them. That will be decided by the balance of gas and dust she can draw to herself in these formative years. If we could listen closely, not with ears, but with instruments sensitive to the faintest motions of matter, we might hear the whisper of her beginning, the slow fall of particles, the gentle stirring of the disk, the hum of energy building in the darkness. It is a whisper older than human memory, a process that has repeated uncountable times in the galaxy and will repeat for eons to come. Each time, it is both the same and entirely unique, shaped by the exact mix of elements, the subtle dance of gravity and motion, the accidents of nearby forces. One day, the whisper will become a voice, a brilliant one that will shine across the void. But for now, Aurelia remains hidden, a promise in the making, a ripple in the cold interstellar cloud that has begun to collapse into something entirely new. Gravity will not release her. The process it has begun will end only when the heat in her heart is enough to push back, when the first flashes of fusion ignite, and she steps onto the grand stage of the cosmos as a true star. Until then, she dreams in darkness, gathering herself for the moment she will awaken. To speak of time in the realm of stars is to loosen our grip on the familiar scales that define human life. On Earth, we measure our existence in years, decades, perhaps a century if fortune allows. We mark the passage of time with birthdays, seasons, and the rhythm of days and nights. A child grows, an adult ages, and the changes are visible. Hair turns silver, faces line with experience, and eventually life draws to a close. It is a span we can hold in our minds, because it is all we have ever known. But to measure time in the life of a star like Aurelia is to step far outside those boundaries, to stretch our imagination until the numbers cease to feel like numbers at all, and instead become abstractions, almost poetry in their vastness. From the human vantage point, Aurelia's birth is glacial. The gathering of her gas and dust, the collapse under gravity, the slow rise of heat within her core, these things play out over hundreds of thousands to millions of years. If we were to compress her formation into the length of a human life, the first decades would pass in near total stillness, nothing to signal the transformation underway. 1,000 human generations could come and go, empires could rise and vanish, ice ages could blanket and retreat from Earth, and Aurelia would still be quietly contracting, only slightly hotter and denser than before. In the human sense of time, she would appear almost motionless. Yet from the universe's perspective, a universe that has been in motion for over 13.8 billion years, this long gestation is little more than an intake of breath. The galaxy has already seen countless stars form and die, has watched entire regions cycle through birth, maturity, and ruin, while Aurelia is still in her infancy. What is 1,000,000 years to something that measures its existence in epochs, in the dance of spiral arms, in the slow collision and merger of galaxies? To the cosmos, Aurelia's life will be one among uncountable others, and the length of it, whether short or long by stellar standards, will pass like the blink of an ancient eye. It is difficult for us to reconcile these two truths, that to us, a star's life feels endless, but to the cosmos, it is fleeting. Our own species has existed for perhaps 300,000 years, a number so small in cosmic terms that it could vanish into the margins of a galactic calendar. Civilization, the thing we most pride ourselves on, is younger still, measured in mere thousands of years. In the time it takes Aurelia just to settle into the stable glow of her main sequence, humanity could live and die 1,000 times over, reinvent itself again and again, lose and rediscover knowledge countless times. If we were to stand at the start of her journey and wait to see her age, we would not endure long enough to witness even the first hint of it. In the quiet of her forming nebula, time itself seems different. There are no ticking clocks, no days and nights. The only markers are changes so slow they would seem invisible to any single observer. The increase in the density of her core, the temperature rising degree by degree over millennia. These are the motions by which a star's clock keeps time. To measure them requires not patience in the human sense, but the kind of patience the universe has in abundance. Patience without expectation, without the need for haste. And yet, even in these grand stretches, there is a kind of urgency. For Aurelia, every moment of gathering and contraction brings her closer to ignition. She does not choose this path. The physics that shape her are inevitable. Gravity will keep pulling, pressure will keep building, and eventually, time will deliver her to the moment when her nuclear heart catches fire. That moment will mark the official start of her life as a star, the point from which her age will be counted. In cosmic terms, the years before that moment are merely prelude, the opening notes before the full symphony begins. Once Aurelia begins to shine, she will measure her life in millions of orbits of her planets, in countless pulses of light traveling outward into the galaxy. To us, her main sequence phase, those long years of steady burning, will seem unimaginably enduring. 1 billion years might pass without noticeable change, her surface still glowing, her spectrum still the same. But that constancy is deceptive. Deep within, her core will be evolving, the balance between hydrogen and helium shifting, the rate of fusion adjusting. For a star, aging is not about the surface appearance, but about the silent transformation in the heart. One of the paradoxes of cosmic time is that it collapses and expands depending on the scale you choose. If we were to compress the universe's history into a single year, the formation of the Earth would occur in early September, life would appear by late September, the dinosaurs would emerge on December 26th, and humans would not arrive until the last few minutes of December 31st. Aurelia's life, however grand, would occupy only a small part of that vast calendar. She might shine for what feels to us like an eternity, yet in the universe's diary, she would be no more than a passage, a single entry in an infinite script. It is humbling to realize that while we speak of eons as incomprehensibly long, the cosmos treats them lightly. To us, 1 million years is beyond imagining. To the galaxy, it is the briefest flicker of motion. Entire star clusters can form, live, and disperse in what, on a cosmic scale, is a short interval. Aurelia's journey from gas cloud to main sequence will be over in the time it takes a spiral arm to drift only slightly along its rotation. If we could observe the galaxy in time-lapse over billions of years, stars like her would seem to appear and vanish like fireflies, blinking in and out of existence against the great dark. And so, the phrase time beyond human measure is not simply poetic, it is literal. Our minds are built to navigate days and years, perhaps centuries. The spans that define a star's life demand a kind of thinking that does not come naturally to us, one that accepts scales so large they feel almost timeless. Aurelia's life will be long enough to see continents shift on distant planets, for moons to drift measurably from their primaries, for civilizations, if they exist, under her light, to rise and fall beyond counting. And yet, the moment she is gone, the universe will continue unchanged, its vast rhythms unbroken, its clock unworried by the loss. From our perspective, it will take her eons to live her life. From the universe's perspective, it will be just a blink. Somewhere between those two truths lies the meaning of her age, not an absolute measure, but a perspective on the brief, bright miracle of her existence. She will not last forever. Nothing does. But in the moment she shines, she will belong fully to the cosmos, as much a part of its endless unfolding as the galaxies themselves. There comes a moment in the hidden darkness of Aurelia's cocoon when the long, slow processes of her formation reach a threshold they cannot retreat from. For millions of years, gravity has been the dominant force, pulling the scattered atoms of hydrogen and helium inward, compressing them into an ever-denser sphere. With each layer that falls toward the center, the weight pressing down increases, the collisions between particles grow fiercer, and the temperature rises to unimaginable levels. What began as a frigid ripple in a molecular cloud has become a hot, spinning mass, its heart now locked in a struggle between the relentless squeeze of gravity and the trapped heat building within. There is no sound here, no crack or roar to announce the change, but the transformation that follows will define Aurelia's entire life. In a fraction of cosmic time, her heart will ignite, and the clock of her age will begin to tick. The physics behind this moment is both elegant and ruthless. As the temperature in her core climbs past 10 million degrees Kelvin, the hydrogen nuclei, protons that have spent billions of years drifting in the galaxy since their creation in the Big Bang, find themselves moving so violently that they can overcome the natural electrical repulsion between them. Under normal conditions, two protons repel one another with stubborn force. Both carry the same positive charge, and their electromagnetic fields push them apart. But here, under such crushing pressure and blistering heat, they are forced so close that the strong nuclear force, the most powerful but shortest ranged of the fundamental forces, can seize them and bind them together. This is nuclear fusion, the alchemy of the cosmos. Two protons merge to form deuterium, releasing energy in the process. That energy radiates outward in the form of gamma rays, photons born in the heart of the star that will eventually work their way to the surface and stream into space as light. This ignition is not a single flash, but a cascade. Once fusion begins, it generates energy, and that energy pushes outward against gravity's inward pull. In the exact balance between these two forces lies the stability of a star. If the outward pressure from fusion falls short, gravity crushes the core further, raising the temperature until fusion strengthens to match it. If the outward pressure becomes too strong, the core expands and cools slightly, slowing the reactions. It is a self-regulating system, one of the most remarkable acts of equilibrium in nature. From this point onward, Aurelia is no longer a collapsing protostar. She is a main sequence star, alive in the only sense the universe recognizes for such things. She is producing her own light and heat through the transformation of matter. The moment of ignition is where astronomers begin counting a star's age. Everything before it, every slow century of gathering dust, every millennia of gravitational contraction, belongs to the prelude, an unmeasured childhood. But with fusion, Aurelia has crossed into her measured life. Her age will now be defined by how long she can sustain the steady burning of hydrogen into helium in her core. For a star like Aurelia, more massive than the Sun, this phase will last perhaps 1 billion years, maybe a little more, long by human reckoning, short by stellar standards. Her greater mass means she burns hotter and faster than smaller stars, living more fiercely but for less time. From her surface, the light now streaming outward will travel in all directions, carrying her signature into the galaxy. Some of it will reach planets forming in the disk around her, worlds still molten or shrouded in thick atmospheres. Some will race past, destined to wander for thousands of years before brushing across the surface of a distant moon or the eyes of some future observer on a faraway world. The photons leaving her today will outlast empires, continents, perhaps even civilizations that might one day arise beneath her light. But for all their seeming permanence, each is just a fleeting product of her burning core, a signal of the reactions taking place deep within. In this new state, the processes inside Aurelia's heart will proceed with relentless precision. Every second, billions of tons of hydrogen will fuse into helium, releasing energy that will sustain her against gravity's pull. The helium, ash, will slowly accumulate in the core, changing its composition and density over time. This is her internal calendar, one that no eye can see directly, but that astronomers can read by studying her spectrum, her brightness, and her subtle oscillations. The ticking of this clock is so steady, so consistent, that it allows scientists to compare stars like Aurelia to theoretical models and determine their ages with surprising accuracy. And yet, despite the magnitude of this transformation, Aurelia herself is unaware. She has no consciousness, no perception of the shift from protostar to main sequence. She is an engine, and now that engine has started running at full power. The laws of physics dictate every beat of her nuclear heart, every photon that escapes, every tremor in her seething plasma seas. From the outside, she has become a point of light in the sky, no different in appearance from the countless other stars scattered across the black. But here, at her birth, we know her story, know that her life has only just begun in a cosmic sense. The beginning of a star's measured age is as much a philosophical boundary as it is a physical one. Before fusion, Aurelia was potential, matter waiting to be transformed, energy locked in the bonds of atomic nuclei. After fusion begins, she is actuality, a source of light, a participant in the galactic cycle of creation and destruction. Everything that will happen in her life, from the stable burning of her youth to the swelling of her red giant phase, to her eventual shedding of outer layers or collapse into a remnant, flows from this single turning point. Without ignition, there is no star, only the ghost of one. So the clock starts ticking, not with a sound, but with light. Light that will travel across the universe, marking Aurelia's place in space and time. In the centuries and millennia to come, she will seem changeless to any who watch her, a fixed jewel in the sky. But deep within, the nuclear fire will be at work, and the helium will pile up grain by grain in her core. Each reaction, each pulse of energy, is one more step along the arc of her finite but magnificent life. From this moment, Aurelia has a birthday, not in the human sense, not marked on any calendar, but in the chronology of the stars. It is the moment when the universe itself recognizes her as one of its luminous children, when her existence begins to contribute to the great stellar symphony that fills the galaxy with light. It is a beginning that has happened trillions of times before and will happen trillions of times again. Yet each is unique. Each is a new flame in the darkness. Aurelia's flame has just been lit, and with it, her story truly begins. In the vast darkness of the galaxy, there are places where the night is not entirely black. From a great distance, these places appear as hazy, luminous clouds suspended in space, their shapes shifting in slow motion over millennia. They are stellar nurseries, regions where the interstellar medium is rich and dense enough to give rise to new suns. These are not gentle cradles, but vast, churning realms where gas and dust writhe under the influence of gravity, turbulence, and the shock waves from ancient explosions. It is within such a nebula that Aurelia now opens her blazing eyes to the universe for the first time. Her surroundings are both chaotic and beautiful. The cloud from which she was born glows in colors invisible to the human eye, the result of nearby newborn stars flooding the region with ultraviolet light. That light excites the atoms in the gas, making hydrogen shine with a soft red hue, oxygen with a ghostly blue-green. Dark filaments of dust wind through this radiance like smoke, concealing pockets where other stars are still gestating, hidden from view. The nebula stretches for dozens of light years in all directions, a vast cosmic tapestry in which Aurelia is but a single point of light. She is not alone. All around her, other stars are forming from the same parent cloud. Some are smaller, dim red dwarfs whose steady burning will outlast Aurelia by trillions of years. Others are massive blue giants, their brief, furious lives destined to end in spectacular supernovae. Each star here has drawn from the same reservoir of material, yet the differences in their masses and compositions will ensure that their destinies diverge widely. The siblings born alongside Aurelia today will not remain close forever. Over millions of years, gravitational interactions and the natural dispersal of the nebula will scatter them across the galaxy, erasing any trace of their shared origin. But for now, they cluster together, shining in the fog like scattered embers in a drifting cloud of smoke. The nebula itself is a relic and a beginning all at once. Its gas and dust are the remains of earlier generations of stars, material flung into space by the winds of dying red giants or the violent deaths of supernovae. Every atom in Aurelia's body has a history. The carbon and oxygen were forged in the cores of ancient suns. The iron came from a star that ended its life in a titanic explosion. Even the hydrogen, the simplest element, was born in the first moments after the Big Bang. This is the great recycling program of the cosmos, where the death of one star seeds the birth of another. In this sense, Aurelia is not the beginning of a story but a continuation, another verse in an endless cosmic poem. Within this nursery, the airless void is anything but still. Stellar winds from the most massive newborn stars carve vast cavities in the gas, shaping the nebula into intricate structures, pillars, arcs, and walls that stretch for light years. Some of these winds strip material away from nearby forming stars, stunting their growth. Others compress the gas, triggering new waves of star formation. Radiation floods the space, creating sharp boundaries where the glowing gas meets the shadowed regions still dense enough to shield themselves from the harsh light. In these shadowed pockets, new stars like Aurelia are still incubating, their futures hidden from the wider galaxy. For Aurelia, the moment of emergence is transformative. Before ignition, she was shrouded in the dust that formed her. Now, her radiation is powerful enough to sweep that dust away, allowing her light to pierce the veil. She becomes visible to the outside universe, not just as a warm infrared glow detectable by sensitive instruments, but as a star in her own right, a source of steady light shining across the cold gulf of space. In the great portrait of the nebula, she is a new point in the pattern, adding to the cluster of luminaries that mark the nursery's heart. The birth of a star within such a nursery is part of a larger rhythm, one that has played out across the galaxy for billions of years. Massive clouds drift between the spiral arms, their shapes and densities changing under the influence of gravity and galactic tides. Some clouds collapse to form stars. Others are torn apart by the same processes. The light from newborn stars illuminates the surrounding gas for a few million years at most, an eye blink in galactic terms, before the winds and radiation disperse the cloud entirely, leaving behind a naked star cluster adrift in open space. Aurelia's nursery will one day vanish, its gas gone, its dust scattered. All that will remain will be the stars it created, bound loosely by gravity until even that bond is broken. In the meantime, this is a place of kinship. Aurelia's light mingles with the light of her siblings, their combined radiance casting a diffuse glow into the depths of the cloud. If there were an observer on a world within this nebula, though such a world could not yet exist, they would see a sky filled not with isolated stars, but with a dense scattering of brilliant points, many so close that their light would blend together. The sky would be alive with color, shifting subtly as dust clouds drift between stars, scattering and filtering their light. There is a strange paradox in this moment. The nursery feels eternal, a realm of endless creation, yet it is inherently temporary. The forces that give it life also ensure its destruction. The same winds and radiation that reveal Aurelia to the universe will, in time, sweep away the very material from which she was born. For now, though, the nebula is vibrant and alive, a stage on which countless stellar stories are beginning all at once. In a few million years, its curtains will fall, and the actors, Aurelia among them, will scatter to the far corners of the galaxy to live out their separate fates. And so Aurelia shines, one among many in this luminous fog, her presence a fresh spark in an ancient process. She is a child of Stardust, born in a place where endings and beginnings are indistinguishable, where the light of creation burns brightly against the cold depths of space. For however long the nursery endures, it will cradle her and her siblings, a brief home in the restless galaxy, until the time comes for each to wander alone. The years that follow Aurelia's birth are a time of quiet but profound transformation. Though she now shines faintly from the heat of her contracting mass, she is still far from the steady blaze of a true star. In the lexicon of astrophysics, she is a protostar, a body caught between the shadow of its formation and the threshold of full ignition. Her nursery still surrounds her, but she is no longer an indistinct knot of cold gas and dust. She is taking on shape, becoming something more compact, more defined, and the forces at work within her are gathering toward a single inevitable moment. From the outside, Aurelia's light is a warm, reddish glow, the product of gravitational energy being converted into heat. As gravity continues to pull her inward, the potential energy of falling material is transformed into thermal energy, raising her temperature both at the surface and, far more critically, deep in her core. This is the Kelvin-Helmholtz process, a slow burn of contraction that will last until the heat in her heart becomes sufficient to ignite nuclear fusion. Unlike the flash and roar of a human fire catching alight, this is an imperceptible build-up, playing out over hundreds of thousands to millions of years. Each passing moment brings her a little closer to the threshold, and the universe, though unhurried, does not allow her to turn back. Her spin, too, is changing. In her earliest days, Aurelia rotated lazily, her immense bulk moving almost imperceptibly. But as her radius decreases, angular momentum forces her to spin faster, just as a skater spins more quickly when drawing in their arms. The once loose envelope of gas becomes an increasingly tight sphere, and the faster rotation begins to shape her structure. Her equator bulges slightly from centrifugal force, while the poles remain more compressed. This spin also stirs her interior, driving currents of plasma that will, in time, help shape her magnetic field. Already, faint magnetic lines of force thread through her surrounding disk of gas and dust, linking her to the material from which she feeds. That disk is both her inheritance and her sustenance. It is composed of the leftover material from the cloud that collapsed to form her, spinning around her like a great flattened ring. Within it, collisions and clumping are already at work, forming the first seeds of planets and moons. But much of the disk's mass will not become worlds. Instead, it will spiral inward along those magnetic pathways, falling into Aurelia and adding to her growing bulk. Each infalling fragment of gas adds to the gravitational squeeze on her core, forcing her interior temperature and pressure higher still. These accretion flows are not uniform. Sometimes great streams of material pour in, brightening her glow, while at other times the flow slackens, allowing the disk to shift and reorganize. Inside Aurelia's heart, the pressure is reaching staggering levels. The atoms of hydrogen are crowded so tightly that they collide incessantly, their motions driven by the relentless compression. Yet, despite the violence of these conditions, the temperature has not yet reached the magic threshold of 10 million degrees Kelvin required for hydrogen fusion to begin. The energy she radiates into space still comes entirely from gravitational contraction, a finite source that will eventually run out. This is the paradox of the protostar stage. She is growing warmer and brighter, yet remains incomplete, a star in waiting. The surrounding nebula is both a shelter and a crucible. Stellar winds from her more massive neighbors scour away some of the gas, gradually thinning the veil around her. At the same time, shock waves from distant events, perhaps a nearby supernova, can jostle her disk, triggering bursts of accretion. These changes leave subtle marks on her developing form, variations in surface temperature, changes in the density of her outer layers, and the shaping of the cavities around her in the nebula. As these winds sweep past, some of Aurelia's own material is lost to space, blown away before it can join her mass. Even now, she is not entirely in control of her fate. The environment in which she was born still exerts its influence. Her rotation and heating give rise to turbulent convection currents within her outer layers. Hot plasma rises from the depths toward the surface, cools slightly, and sinks again in great looping flows. These convection cells churn endlessly, carrying heat outward and mixing the gases within her. They also twist and stretch her magnetic field, creating spots on her surface where energy escapes more slowly, forming dark patches when compared to the surrounding glow. These star spots are the youthful marks of a protostar, signs of her restless magnetic activity. Occasionally, flares erupt from her surface, releasing sudden bursts of energy into the space around her. These flares can ripple through her disk, briefly altering the orbits of dust and gas, a reminder that she is already capable of affecting her surroundings in powerful ways. The timescale of these years is almost incomprehensible. From a human perspective, Aurelia's changes seem frozen in place. Thousands of years could pass without the slightest difference visible to the naked eye. And yet, the transformation is constant beneath the surface, the steady rise of her core temperature marking the progress toward a moment that will alter her forever. If we could speed up time to watch her life like a film, we would see her shrinking steadily, spinning faster, her light shifting subtly toward the bluer end of the spectrum as she grows hotter. The gas and dust in her disk would swirl inward, bright arcs of infall punctuating her youth, until at last the core reached the ignition point and her life as a true star began. Even in this stage, the universe is at work weaving connections. The atoms falling into Aurelia will one day be carried outward again in her light, perhaps to seed another star's birth millions or billions of years from now. The hydrogen she now holds will be transformed into helium, then into heavier elements, until those two are cast into space at the end of her life. The protostar years are, in a sense, the drawing of breath before the song begins, a slow inhalation that gathers the energy for the long, luminous exhalation to come. Eventually, the disk will thin, its matter either consumed by Aurelia, ejected by her winds, or locked into planets, asteroids, and comets. As the last of the heavy infall subsides, she will become increasingly isolated, her shape and brightness stabilizing. Deep inside, the temperature will continue to climb toward the threshold, and then, in a moment that will not be seen from outside but will change her entirely, fusion will begin. The first reactions will be tentative, quickly balanced by the surrounding pressure, but they will mark the end of the protostar years. The energy from these reactions will be enough to halt further contraction, holding her in a perfect balance between gravity and the outward push of radiation. When that moment comes, Aurelia will have crossed a boundary as sharp as any in her long life. The slow, unseen preparation will be over, replaced by the steady, blazing constancy of the main sequence. But these protostar years will remain imprinted on her, in the rotation rate she carries into adulthood, in the planets that may form around her, in the scars left by her turbulent youth. For now, she continues to contract, to heat, to spin, her core just shy of the fire that will define her. She waits without awareness, the laws of physics guiding her toward her destiny, her first true breath as a star just ahead. The moment of ignition comes without fanfare, without an external signal to announce its arrival, yet it changes everything. Deep within Aurelia's core, the relentless pressure has at last pushed hydrogen atoms into such intimate proximity that their mutual repulsion collapses under the grip of the strong nuclear force. In an instant, protons fuse, forming helium nuclei and releasing a torrent of energy in the form of gamma-ray photons. This is the dawn of her true stellar life, the moment astronomers call the arrival on the main sequence. Gravity, which has been tirelessly compressing her for millions of years, now meets its match in the outward push of fusion-generated radiation. The balance, delicate yet robust, locks into place, and for the first time, Aurelia is in equilibrium. From this point onward, she becomes something the universe recognizes as a star in full. Her luminosity steadies, no longer driven by the slow contraction of her youth, but by the continuous alchemy at her heart. In the core, the proton-proton chain runs endlessly. Hydrogen into helium, helium into energy, energy into light and heat that flow outward through her layers. The photons born in her core will scatter and dance through her dense plasma for tens of thousands of years before escaping into space, where they will travel unimpeded across the cosmic gulf. Every second, countless trillions of hydrogen nuclei merge into helium, a steady, almost meditative rhythm that will define billions of years to come. This new stability is both a shield and a stage. The furious inward crush of gravity is held at bay by the radiation pressure from her core, and so Aurelia's size stabilizes. Her temperature at the surface settles into a range determined by her mass and composition. Her color shifts toward a golden-white glow. She now radiates a steady beacon of light into the dark, an energy source that could, in time, nurture the rise of life on any world circling her. Around her, the remnants of her protoplanetary disk have already begun to consolidate into planets, moons, asteroids, and comets. The winds and radiation streaming from her surface shape this emerging planetary system, sweeping away lighter gases from the inner worlds, sculpting their orbits, and perhaps sparking chemical reactions in their nascent atmospheres. On the planets closest to her, the light that began in her core tens of thousands of years earlier now arrives each day with unerring consistency. Aurelia's main sequence years are a time of peace compared to the chaos of her birth. Though storms still flare on her surface, arcs of plasma leaping thousands of kilometers into space, they are minor punctuation marks in a long, steady song. Her output varies so little over millions of years that the climates of her planets can develop long-term stability, allowing oceans, atmospheres, and perhaps even life to take hold. If observers could evolve on one of these worlds, they would come to think of Aurelia as eternal, a fixture in their sky whose warmth and light are as constant as the passage of time itself. Beneath this apparent serenity, the processes that sustain her are immense in scale and unyielding in demand. The hydrogen in her core is finite, and with every passing second, more of it is transmuted into helium. Over billions of years, the composition of her heart changes. Helium ash accumulates, gradually increasing the mean molecular weight of the plasma and causing the core to contract slightly. This contraction, in turn, raises the temperature, and as the temperature climbs, the rate of fusion increases. It is a slow feedback loop, imperceptible over the span of a human life, but inevitable across geologic time. As the fusion rate rises, Aurelia will grow gradually brighter, subtly shifting the conditions in her system. For planets close to her, this slow brightening could one day tip climates toward instability. For now, though, these changes are so incremental that they might as well not exist to any creatures who might call her light their own. The bulk of her main sequence life will be spent in this state of equilibrium. where hydrogen fusion in the core balances gravity's pull. This is the long summer of a star's life, a span of stability and abundance during which she is neither too young and tempestuous nor too old and unstable. In galactic terms, she is in her prime, at the perfect balance point between energy generation and structural stability. From afar, she is one among billions, indistinguishable from her peers to the naked eye. Yet every star is unique in its subtle details. In the exact proportion of heavier elements she inherited from her parent cloud, in the specific arrangement of her magnetic fields, in the rhythms of her surface activity. These differences shape her planetary system, influencing which worlds retain atmospheres, which are bathed in gentle warmth, and which are scoured by intense radiation. Her magnetic field, generated by the churning motions of her plasma, helps protect nearby worlds from cosmic rays and her own stellar wind, shaping the space environment around her. The light of Aurelia's long summer will carry across vast distances, perhaps eventually falling on the dust and ice of faraway comets or on the surfaces of moons orbiting gas giants in her system. In the dark outer reaches, her glow is faint but still the dominant source of heat and illumination. Over the eons, those outer bodies may be perturbed by the gravitational influence of passing stars, sometimes plunging inward toward her warmth, carrying with them the raw materials for chemical complexity to inner worlds. In this way, her influence extends far beyond the reach of her visible light, shaping the destinies of every object bound to her gravity. Though she is stable, she is not static. Subtle pulsations and cycles move through her body, changes in magnetic activity that may wax and wane over years or decades. These cycles might occasionally intensify, sending bursts of charged particles toward her planets and painting their skies with auroras. For any life that might exist there, such events could be both a wonder and a hazard, reminders that their star, though steady, is still a living, dynamic object. As the centuries and millennia accumulate into millions of years, Aurelia's role in her corner of the galaxy becomes fixed in the grand pattern. She orbits the galactic center alongside countless other stars, drifting through spiral arms, sometimes passing near clusters or nebulae. From her perspective, these changes are glacial. Her light shines the same on each rotation of the galaxy, even as the stellar neighborhood slowly shifts. Her planets may watch unfamiliar constellations rise and set over epochs, but Aurelia herself remains the constant. The energy she pours into space sustains more than just warmth. It is a constant outward message, a signature written in photons that could be detected from across the galaxy. In this way, she is part of a conversation older than life itself, a chorus of stars singing their existence into the void. Some of those photons will wander endlessly, crossing billions of light years, perhaps never touching matter again. Others will fall onto dust grains, onto the frozen shells of distant comets, or onto the leaves of alien plants, if such plants exist in her system, powering photosynthesis, feeding ecosystems, and driving the cycle of life. For Aurelia, there is no awareness of the gift she offers. She simply exists in balance, her hydrogen burning steadily, her outer layers bathed in the energy of her core. This phase will be, by far, the longest chapter of her life, outlasting the formation of her planets, the rise and fall of any civilizations that might dwell there, and perhaps even the orbits of those worlds themselves. It is a time of abundance, a time when her warmth and light are given freely, when she appears to be unchanging and eternal. Yet the seeds of change are already within her, hidden in the slow build-up of helium at her center. One day, far in the future, that balance will shift, and the long summer will draw to a close. The transformation will be slow at first, then rapid, as gravity once again begins to dominate over the waning power of her core. But for now, Aurelia is a star in her prime, her life stretching ahead for billions of years, her light constant in a universe where so much is fleeting. She is the quiet heart of her system, the anchor for worlds and dreams alike. And for this long span of cosmic time, she will burn in serene majesty, holding the dark at bay. Mass is destiny for a star, the fundamental trait that decides every major chapter of its existence. From the moment Aurelia's core first ignited, the number that defined her fate was not her age or her luminosity, but her mass, twice that of the sun. In cosmic terms, this placed her in a category of stars that burn hotter, shine brighter, and live faster than their smaller counterparts. It is a paradox of stellar life. The more mass a star holds, the more furiously it must consume its fuel, and the shorter its time in the main sequence. A star like the Sun can enjoy around 10 billion years of steady fusion. Aurelia will have only about a quarter of that time before her reserves of hydrogen are too diminished to sustain her balance. The reasons lie deep in her core. Twice the mass means a much greater gravitational pull, which compresses her core to higher pressures and temperatures than in a smaller star. That extra heat accelerates the fusion process dramatically, allowing hydrogen atoms to overcome their mutual repulsion far more readily. But this speed comes at a cost. She is spending her fuel budget recklessly, her internal fires blazing through hydrogen at a rate that will, in cosmic terms, bring her to maturity and old age almost before some of her less massive peers have even settled into middle life. If we could somehow compare stellar biographies, Aurelia's would be a brilliant novella, while a smaller red dwarf might produce a slow, sprawling epic spanning trillions of years. Her mass not only dictates her lifespan, but also her temperament. The higher core temperature means Aurelia radiates more intensely across the electromagnetic spectrum, with stronger ultraviolet emissions than a smaller star. This radiation shapes her system in ways subtler and harsher than the Sun's influence on our solar system. Planets too close to her might have their atmospheres stripped away more easily. Water might be driven off before it ever has a chance to collect in oceans. Even the habitable zone, the delicate region where temperatures permit liquid water, sits farther out from her than it does around the Sun, yet still faces stronger flares and bursts of stellar wind. Life, if it emerges here, would have to contend with a brighter, more intense sky, and possibly a harsher radiation environment. The greater mass also affects her structure and internal dynamics. In smaller stars like the Sun, energy moves outward from the core partly through radiation and partly through convection. Huge bubbles of plasma rising and falling in a slow, seething churn. Aurelia's hotter, more massive nature reduces the role of convection in her outer layers, allowing radiation to carry much of the energy outward directly. This subtle difference influences her magnetic activity and the way her surface behaves over time. Fewer convective motions can mean different cycles of magnetic field generation, perhaps leading to longer or more irregular patterns of surface activity. There is also a beauty to her mass-driven brightness. In the spiral arm of her galaxy, she is more noticeable than the Sun would be at a similar distance. To a civilization orbiting another star, Aurelia might appear as a white gold point of light, steady and slightly more luminous than the average in her neighborhood. If they had sensitive enough instruments, they could learn her mass from her spectrum and brightness, and from that figure, they could already predict the broad strokes of her destiny. An early but spectacular death, a transformation into something smaller, denser, and stranger than the star she is now. For all her brilliance, Aurelia is still careful in her balancing act. Her gravitational pressure and radiation pressure remain matched for now, but the greater pace of her fusion means the slow drift toward imbalance will come sooner than for a lighter star. Already, helium is accumulating in her core, the ash of fusion that does not itself contribute to energy generation at these temperatures. In a less massive star, The helium might remain inert for billions of years more, but in Aurelia, the rising temperatures will eventually be enough to ignite helium fusion not long after the hydrogen runs out. This helium flash in more massive stars is less of a sudden explosion and more of a graceful but rapid transition into a new fusion phase, one that will alter her size, color, and luminosity in dramatic ways. Mass determines even the manner of her aging. A small star's red giant phase is a slow, gentle swelling. Aurelia's will be quicker and grander, her envelope expanding to hundreds of times her current radius in just a few million years once the process begins. Her outer layers will cool and redden, transforming her from the brilliant white gold of her youth to the deep crimson glow of a giant. For any worlds orbiting close to her now, this will be a catastrophic change. Planets once basking in her steady warmth will be engulfed, vaporized, or left charred under her swollen, cooling surface. Yet this same mass that shortens her life also grants her an ending of greater drama. Stars of Aurelia's mass occupy a middle ground in stellar evolution. She is not massive enough to go supernova, tearing herself apart in a cosmic blaze, but she is heavy enough to shed her outer layers in spectacular planetary nebulae, illuminating space with intricate shells of glowing gas. Her core, too small to collapse into a neutron star, but too large to simply fade quietly, will become a white dwarf, a diamond-like remnant that will slowly cool for trillions of years, a silent ember marking the place where Aurelia once blazed. Her mass even shapes the company she keeps. In her youth, she might have formed alongside other stars of varying sizes, but the most massive among them will already be gone long before her own final act. The smaller stars in her birth cluster, meanwhile, may still be in the prime of their main sequence lives when she dies. If any of her stellar siblings survive in her vicinity, they will watch her transformation from main sequence to giant to white dwarf in what, for them, might feel like the blink of an eye. In the broader galactic ecology, stars like Aurelia play an outsized role despite their relatively brief lives. Their higher luminosity and stronger stellar winds contribute to the chemical enrichment of the interstellar medium. When she eventually casts off her outer layers, she will return elements like carbon, nitrogen, and oxygen to the galaxy, elements that smaller stars take far longer to release. This is part of the irony of her destiny. Though her life is shorter, her legacy in seeding the building blocks of planets and life may be richer and more immediate than that of longer-lived but quieter stars. As she orbits the galactic center, she does not know that her path and her timetable are already written in her mass. Every gram of her being participates in a complex negotiation between gravity and fusion, between collapse and expansion, but the terms of the agreement are fixed. Twice the mass of the sun means a youth of blazing brightness, a maturity of intense but relatively brief stability, and an old age of rapid transformation. Compared to the universe itself, her life will be over in an instant. Compared to a human life, she is practically eternal. And yet the difference between practically eternal and truly eternal is everything in the life of a star. For now, her brilliance continues without falter, her planets still circle in their ordained paths, and her hydrogen stores still hold out against the inevitable. But the fuse is burning faster than it would for a smaller star. The day will come when the balance tips, when the weight of her own mass accelerates her decline, and when she trades the steady song of her main sequence life for the swelling, turbulent crescendo of her final acts. Mass has already determined that ending. All that remains is for time to carry her there. Deep within Aurelia, far beneath her luminous surface, lies a world no human eye will ever see, yet one that shapes everything she is. Her true life, her energy, her brilliance all begin in this hidden heart, the core, where matter exists in a state beyond anything imagined in the quiet cold of the surrounding universe. Here, temperatures reach tens of millions of degrees, and pressures are so immense that the very nature of atoms changes. The electrons are stripped away entirely, leaving bare nuclei adrift in a sea of charged particles, moving and colliding at speeds dictated by such extreme heat. It is a realm where ordinary rules bend, where hydrogen atoms, which under any other conditions would fiercely repel one another, are pressed together by the overwhelming grip of gravity until they fuse into helium. This is nuclear fusion, the alchemy of the stars, and it is what keeps Aurelia alive. Every second, billions upon billions of hydrogen nuclei combine, their mass transforming into energy according to Einstein's elegant equation. The process releases photons, packets of light energy, along with other subatomic particles that carry away some of the energy in forms invisible to our eyes. The light born here does not rush immediately to freedom. In fact, its journey outward is so difficult and chaotic that any given photon may take thousands, even millions, of years to escape from the core to the surface. In the heart of a star, light moves not in a straight line but in an endless zigzag, scattering off particles, absorbed and re-emitted countless times before it makes any real progress. Around the core lies the radiative zone, a vast layer where the temperature and density remain high enough that radiation is the dominant means of transporting energy. In this region, photons are constantly jostled and redirected by a dense fog of ions, each step forward immediately undone by a scattering event. If one could somehow follow a single photon from its birth, the path traced would be less aligned and more like the scribbles of a restless child, looping back on itself thousands of times in an eternal maze. The energy trickles outward at an absurdly slow pace, yet there is no urgency here. Fusion in the core runs continuously, replenishing the supply of photons as others crawl their way outward. Farther still from the core, in stars like Aurelia, the radiative zone eventually gives way to the convective zone. This is where the density and opacity of the stellar material increase enough that photons can no longer efficiently carry the energy. Instead, the hot plasma itself begins to move in great, slow currents, vast columns of material heated from below rising toward the surface, cooling, and then sinking again. These convective motions are unimaginably large, each cell of movement perhaps as wide as the Earth itself, but in the context of the star they are small-scale ripples on a giant's skin. This churning not only moves energy outward more efficiently, but also stirs the star's material, helping to mix elements created in fusion back into the outer layers. The interplay between fusion in the core, radiative transfer in the middle layers, and convection nearer the surface creates a complex internal symphony. It is not static. Subtle changes in core temperature, pressure, or composition can alter the balance, affecting how energy is transported and how the star behaves at its surface. For Aurelia, whose mass gives her a hotter and denser core than the Sun, the radiative zone is larger and more dominant, while her convective region near the surface is shallower. Still, that thin outer convective zone plays a role in generating her magnetic fields through a dynamo effect, where the movement of charged particles in the rotating star creates vast loops of magnetic force extending far into space. All the while, the core continues its relentless work. Hydrogen is converted into helium at a rate that boggles the mind. In the time it takes to read a single sentence, Aurelia has fused millions of tons of matter into energy. And yet, despite this furious pace, she remains steady. The delicate balance between gravity pulling inward and radiation pressure pushing outward ensures that she neither collapses under her own weight nor explodes into space. This equilibrium is self-regulating. If the core heats up too much, it expands slightly, reducing the pressure and cooling down. If it cools too much, it contracts, heating again. Such stability is why main sequence stars like Aurelia can shine so steadily for millions or billions of years without sudden, violent changes. But even in such steadiness, time is at work. Every fusion reaction turns 4 hydrogen nuclei into 1 helium nucleus, slightly more massive than the sum of its parts in terms of particles, but lighter in mass due to the energy released. Over eons, the core slowly fills with helium, ash, that does not participate in the current fusion process. As the hydrogen fuel in the very center is exhausted, fusion moves to a surrounding shell, and the balance in the heart of the star begins to shift. For now, in Aurelia's youth and middle age, the change is slow, imperceptible to an outside observer. But deep inside, the ratios of hydrogen to helium are steadily tipping, setting the stage for the transformations to come. The photons born in her core, after their long and tortuous journey outward, finally break free at the surface as visible light, ultraviolet rays, and other forms of radiation. This is the light that spills into space, illuminating any nearby worlds, warming their surfaces and shaping their climates. It is strange to think that much of the light we see from Aurelia today began its journey long before any current events on those worlds unfolded, perhaps before some of those planets even formed. In this sense, the surface of a star is not only its present self, but also a messenger of its deep past. Though her light takes years to travel to distant corners of the galaxy, the energy that sustains her planets and defines her presence in the sky began as raw mass in her core, reshaped by fusion into something intangible yet powerful. This process will not last forever. Hydrogen is finite, and each second brings Aurelia a fraction closer to the day when fusion in her core will falter. But for now, her hidden heart works without pause, indifferent to the timescales of human lives or even civilizations. The interior of a star is one of the most inaccessible places in nature, yet through the study of vibrations on her surface, subtle oscillations caused by sound waves trapped within her structure, astronomers can infer details about what happens inside. These starquakes reveal information about temperature, density, and composition, a distant echo of the hidden work being done in her depths. If Aurelia could speak, she would not tell her story in words but in the ripples of her light and the rhythms of her pulsations, carrying the signature of her internal processes across the gulf of space. And so, beneath her radiant exterior, Aurelia's core continues its patient labor, weaving light from matter, turning the simplest element in the universe into energy that will one day scatter across the galaxy. It is a hidden forge, constant yet always changing, whose work shapes not only her own destiny but the fate of any worlds in her care. Every flicker of light that escapes into the night sky is the end of a journey begun here, in the heart where fusion and convection dance their slow, eternal dance. The first signs of change come so gradually that, from the perspective of any life orbiting Aurelia, they are imperceptible for generations. For billions of years, she has been a model of stability, her light steady, her warmth unchanging. But deep in her heart, the balance she has so long maintained begins to tip. The hydrogen in her core, the fuel that has sustained her brilliance, is running low. Layer by layer, reaction by reaction, the store has been consumed, replaced by a dense sphere of helium, ash, that cannot yet be burned. The processes that have defined her life up to this point are now approaching their limit. The shift begins invisibly. As the last hydrogen atoms in her core fuse into helium, the rate of energy production in that central region drops. Without the outward pressure from fusion to perfectly counter gravity, the core begins to contract under its own weight. This contraction releases gravitational energy, heating the core even further. In the shell of hydrogen that surrounds the inert helium center, the temperature rises high enough for fusion to resume, not in the heart itself, but in this narrow band where conditions are still favorable. Shell fusion is more vigorous and less self-regulating than the core fusion that came before, and it begins to flood Aurelia with energy at a faster rate than ever before in her life. The increased energy production has an unexpected effect. Instead of growing hotter at the surface, Aurelia's outer layers expand. Her photosphere swells outward, and as it does, it cools. The star that once shone with a steady white-gold brilliance begins to shift toward a deeper, warmer hue, her light reddening slightly. To the casual observer, she might appear larger and more luminous, yet softer in color. This is the early stage of her metamorphosis into a red giant, though she is not yet at her most dramatic form. This expansion also slows her rotation. For much of her life, Aurelia has spun gracefully, her rotation influencing the distribution of magnetic fields across her surface. As she grows in size, that spin rate decreases, much like a figure skater extending their arms. The once dynamic interplay of magnetic activity begins to alter, star spots and flares change in pattern and frequency. Her magnetic field may weaken in overall strength, allowing stellar winds to flow more freely into space. These winds, carrying streams of charged particles, will play a greater role in her later life, stripping away mass bit by bit. The instability at her surface is subtle now, but increasing. The swelling of her outer layers makes them more loosely bound to the core's gravity. Convective motions grow more chaotic, rising and falling with greater vigor, causing fluctuations in brightness that may be detectable to distant observers. In her younger days, convection was orderly and restrained. Now, with the outer layers puffed up and tenuous, the granulation pattern on her surface becomes larger and more pronounced. Gigantic convective cells may dominate the photosphere, each one spanning a significant fraction of her diameter. Within her, the helium core continues to shrink and grow hotter under the pressure of its own weight. This is a dangerous process, for the temperature is approaching the threshold at which helium itself can ignite in fusion, transforming into carbon and oxygen. But that moment is not yet here. For now, the helium remains inert, while the shell burning of hydrogen drives her expansion and instability. Every passing million years brings her closer to the tipping point. For the worlds that may orbit her, these changes are not academic. As Aurelia swells, the increased luminosity pours more energy into her system. Planets once comfortably temperate may now be scorched, their atmospheres stripped away or transformed by heat. Moons of distant giants might thaw from frozen shells into seas of liquid, briefly becoming habitable in this transient warm period. The architecture of her planetary family will be reshaped not by collision or impact, but by the simple, relentless evolution of their parent star. Out in the surrounding space, the stronger stellar winds carry away more than just particles. They carry with them pieces of Aurelia herself. Over time, these winds enrich the interstellar medium with material forged during her life. Heavier elements created in her fusion processes, as well as dust that may someday seed new planetary systems. Even before her death, Aurelia is beginning to give back to the galaxy from which she was born. The instability is not only physical, but rhythmic. Stars approaching the end of their hydrogen-burning phase often begin to pulsate faintly. Aurelia's radius may oscillate over timescales of days, weeks, or months, the expansions and contractions altering her brightness. This is the star's own heartbeat, the result of complex feedback between energy production, temperature, and pressure. While imperceptible to any nearby life without advanced observation, these pulses are clear signals to astronomers watching from far away. Aurelia's youth is over. In her hidden depths, the pressure on the helium core is building towards something extraordinary. Helium fusion, when it begins in stars of Aurelia's mass, will not start gently. It will ignite in what astronomers call a helium flash, a runaway process that releases an enormous amount of energy in mere minutes. Yet paradoxically, this titanic event will happen entirely within her interior, with almost no immediate effect visible at her surface. She will carry on shining, unaware to the casual eye of the drama that has just unfolded within. But the helium flash lies just ahead. The current phase is the quiet tension before the storm. For now, Aurelia continues her transformation slowly, her surface growing larger, her color deepening. Her gravitational hold on her outer layers weakens, and the balance she has maintained for billions of years is slipping beyond recovery. She is entering a phase of her life in which each change accelerates the next, an inevitable slide toward a very different existence. She is not dying, not yet, but she is no longer the star she once was. And still, to many, she would seem ageless. From a human perspective, these transitions play out over such immense spans of time that they could be mistaken for permanence. Civilizations might rise and fall under her light without ever realizing she is changing. Yet in the silent ledger of the cosmos, the numbers are being added up. The hydrogen reserves are nearly spent, the pressure on the core is mounting, and the future is already written in the physics that governs her being. Aurelia is poised at the brink of her next great transformation. Her long summer is over. Ahead lies an autumn of swelling size and deepening hue, a time when she will cast her light farther and warmer than ever before, even as the forces within her conspire to bring that chapter to an end. The signs of age are written in every layer of her being, from the restless currents in her surface to the tightening grip of gravity around her heart. And soon, they will be impossible to ignore. The transformation, long in the making, finally surges into reality. Aurelia's outer layers billow outward, the subtle swelling of earlier ages giving way to an almost unstoppable expansion. From a star of moderate size, she becomes a colossus, her photosphere extending hundreds of times farther than it did during her main sequence years. Once, she might have comfortably fit between the Sun and the orbit of Mercury. Now, she could engulf the orbits of planets that had once seemed distant from her heart. This is the reign of the red giant, a season of grandeur and instability. Her light, once white gold, now blooms into a rich, warm crimson. The deepening hue is the signature of a cooler surface. Despite her vast increase in total luminosity, the immense size of her photosphere spreads her energy over a far greater area. But to the eye, she is brighter than ever. Her light washes across the system in waves of gold and red, a fire that cannot be ignored. To any surviving observers on worlds still orbiting at safe distances, Aurelia is both magnificent and terrible, her beauty inseparable from the forces that will unmake their familiar sky. Within her, the helium flash has come and gone, an invisible, internal ignition that reshaped the balance of her energy production. In her core, helium now fuses into carbon and oxygen, releasing vast quantities of energy. Around this core, a shell of hydrogen still burns, adding to the overall luminosity. The combination of these processes floods Aurelia with energy, more than her previous structure could contain, and so she has expanded into her new form. The gravitational tether between her surface and her center is weaker now. The outer layers drift with a looseness that makes them vulnerable to the constant flow of stellar winds. These winds are no longer gentle. Aurelia's expanded surface loses mass at a staggering rate, casting a steady stream of gas and dust into the void. This material forms an extended atmosphere around her, a tenuous, glowing shroud that may stretch for millions of kilometers beyond her visible surface. In time, these outflows will create complex, layered shells of gas, enriched with the products of her fusion processes. To the galaxy, this is a gift. The elements forged in her life will one day become part of new stars, planets, and perhaps life itself. The view from afar is one of awe. The red giant phase is a brief but striking episode in a star's life, and Aurelia wears her crown with both elegance and power. She dominates her region of the galaxy, outshining younger, smaller stars nearby. Any remaining sibling stars from her nursery are now widely scattered, and few could match her brilliance at this moment. But her reign is not one of stability, it is a reign of change. Every 1,000 years, she loses more of herself to the winds. Every million years, her structure subtly shifts as the core processes consume their fuel and alter the balance yet again. Inside her vast convective envelope, heat and matter churn in currents so immense that each could contain dozens of Earths. Convection carries material from near the core outward, dredging up newly forged elements to the surface in what astronomers call dredge-up events. This mixing can alter the composition of her outer layers, changing the spectral signature of her light. To a spectroscope, Aurelia's crown is not just red. It is chemically rich, marked with the fingerprints of carbon, nitrogen, and oxygen that have never before seen the light of day. Planets that once orbited safely in Aurelia's habitable zone are gone now, swallowed or scorched. If any worlds remain at the system's far reaches, they are transformed by the influx of energy. Icy moons awaken as subsurface oceans melt, only to lose their atmospheres to the fierce winds. Distant comets, stirred from their cold storage, race toward the giant star, their tails vast and luminous in her ruddy glow before they disintegrate. The architecture of her system is no longer a quiet set of predictable orbits, but a place of upheaval and dispersal. The outer crown of Aurelia's atmosphere is not static. It pulses and ripples with the star's own internal rhythms. Some of these pulsations are gentle, a steady in and out breathing of her surface. Others grow violent, causing temporary surges and mass loss. In moments of particular instability, the winds may intensify into gusts that expel entire layers of gas into the surrounding space. These ejections can briefly form spectacular arcs and knots of glowing material around the star, sculpted by the interplay of wind, gravity, and magnetic fields. From a cosmic perspective, this phase is fleeting. Stars like Aurelia, twice the mass of the Sun, spend billions of years on the main sequence, but only a few tens of millions in the red giant stage. Yet in that short span, the star undergoes some of the most dramatic changes of her entire life. Every moment is an acceleration toward the inevitable, the exhaustion of her helium fuel and the collapse of her fusion processes. When the helium is gone, the carbon-oxygen core will contract once more, and the outer layers, already loose and fragile, will be cast off entirely. But for now, Aurelia still burns, her expanded form sustained by the fire within. There is a paradox to her reign. To those who know the fate of stars, Aurelia's glory is a prelude to loss. But to the galaxy at large, her crown is a beacon, a declaration of vitality. The gas and dust streaming from her surface are already mingling with the interstellar medium, carrying the story of her life outward in a way that will long outlast her physical form. The very atoms that once formed her will one day belong to other suns, other worlds, perhaps even other beings who will look to the stars and wonder about their origins. The red giant's crown is not a fixed jewel, but a flowing, ever-changing halo, made not of gold but of stardust and light. Aurelia wears it with the dignity of a monarch whose reign is bound by the rules of nature, not the will of subjects. Her transformation has made her vast, luminous, and fragile all at once, a giant whose life force both sustains her majesty and assures its eventual end. And so she continues, her light spilling into the dark, her winds scattering the seeds of the future. The reign will end soon in cosmic terms, but for now, Aurelia stands at the height of her splendor, a star in her fullest bloom. In the silence of space, she is a crimson monarch, crowned not by metals or gems, but by the legacy she is even now creating with every breath of stellar wind. The end approaches not with a sudden catastrophe, but with a slow, inevitable loosening of Aurelia's hold on herself. The great red crown she has worn begins to thin, each gust of her stellar wind carrying away more of her outer layers. The expansion that once seemed majestic now becomes fragile, the vast shell of gas around her sustained less by the heat of fusion and more by the inertia of its own escape. This is no supernova, no final, thunderous outburst. For a star of her mass, death is not a single moment. It is a prolonged surrender. Within her core, the helium that has fueled this last stage of her life is dwindling. The triple alpha process, helium atoms fusing to form carbon, has been running for millions of years, and it now begins to falter. The temperatures and pressures are still immense, but without a steady supply of fuel, the reactions slow. Surrounding the carbon-oxygen core, shells of helium and hydrogen still burn in layered fusion zones, but the balance between these shells and the swelling envelope above grows unstable. The energy they release pushes at her surface in pulses, each one a little stronger, each one shaking more material free into space. The mass loss accelerates. At first, it was a steady wind, then a strong breeze, but now it becomes a near-continuous outflow. Vast quantities of gas flow away at speeds of tens of kilometers per second, carrying with them dust grains, microscopic crystals of carbon and silicates formed in the cooling outer layers. These dust grains scatter Aurelia's light, creating a soft halo that makes her appear even more ethereal to any distant observer. The wind is no longer a background process. It is the central act of her final stage. As more layers drift away, the space around Aurelia begins to change. The gas she has shed does not simply vanish. It forms a slowly expanding bubble around her, enriched with the elements her fusion furnaces have created over billions of years. The light from her core illuminates this shell, causing it to glow in delicate shades of green, blue, and red. The shapes are not smooth. The gas is sculpted into arcs, knots, and filaments by the interplay of gravity, magnetic fields, and the very wind that carried it out. This is the birth of her planetary nebula, a structure so named not because it has anything to do with planets, but because early astronomers saw such glowing orbs through their telescopes and mistook them for distant worlds. In these final hundreds of thousands of years, Aurelia becomes even more beautiful. She is shrinking now, not her outer shroud, but her true self, the hot core emerging from beneath the fading envelope. As the core becomes exposed, its temperature soars, and the ultraviolet radiation it emits ionizes the surrounding gas. This ionization causes the nebula to shine, its colors determined by the elements within. Oxygen glows green, hydrogen red, nitrogen pink. To the human eye, it would be a vision of astonishing delicacy, a luminous cloud suspended in the void, the last visible testament to Aurelia's life. Yet the beauty hides the truth. Aurelia herself is almost gone. The carbon-oxygen core at her center is no longer sustaining fusion. It is simply cooling under the pressure of its own gravity. But the collapse is halted by a strange quantum phenomenon, electron degeneracy pressure, which prevents the core from shrinking further. This remnant is tiny compared to her former glory, barely the size of Earth, but it contains most of her mass. The planetary nebula will expand for tens of thousands of years before it disperses into the interstellar medium, leaving behind only this remnant, a white dwarf. For the worlds that may once have orbited her, this is the final dispersal of the familiar sky. Any planet within her reach has long since been engulfed or stripped bare, and those farther away now drift in a transformed system. Where once Aurelia was the dominant presence, a brilliant and steady source of warmth, there is now a glowing ghost surrounded by an ever-thinning veil. In time, Even that veil will fade into the background of the galaxy, indistinguishable from the interstellar clouds that gave her birth. The farewell is gentle by stellar standards, yet it is absolute. Aurelia will never burn again. Her nuclear furnaces are cold. What remains is the memory of her life written into the atoms she has cast off. The carbon and oxygen in her nebula will someday be swept into new molecular clouds, where gravity will gather them into new stars, new planets, and perhaps new living beings who will look to the heavens and wonder about the ancient star whose atoms they now carry within themselves. From a cosmic vantage point, this ending is not a tragedy, but a transformation. Aurelia's death is the mechanism by which the galaxy enriches itself. Without stars like her, the universe would remain a place of only hydrogen and helium, barren of the heavier elements that make complex chemistry and life possible. Her farewell is a gift, one that will resonate far beyond the time when her light fades. Even as her nebula expands and thins, astronomers on distant worlds might look upon her and record her spectrum, noting the signatures of her elements, piecing together the story of her life. They might not know her by name, but they would know her by her crown of gas, her quiet shedding of layers, and the hot white heart that glows at her center. They would know she was once a giant, and that she chose, though not by will, to end not in fire and violence, but in a slow, luminous release. In her final visible form, Aurelia is a paradox, smaller than she has ever been at her center, yet surrounded by the largest and most delicate structure she has ever created. Her nebula is a work of art shaped by physics alone, a testament to the fact that beauty in the universe often arises not from permanence, but from change. For tens of thousands of years, an instant in cosmic time, she will remain a lantern in the darkness, her light passing through the gossamer veil she has cast off. And then, slowly, the veil will fade, the light will dim, and only the white dwarf will remain, cooling silently for billions of years. Her farewell is not marked by violence, but by generosity. She leaves behind not destruction, but creation, the raw materials for the next generation of stars and worlds. Aurelia's story, like all stellar stories, is one of cycles, from cloud to star, from star to nebula, and from nebula back to the cloud. She is gone, but her essence is scattered into the galaxy, ready to be reborn. What remains of Aurelia is no longer a star in the traditional sense, but the dense, glowing ember of a white dwarf. She is small beyond expectation, no larger in diameter than Earth, yet holding more than half of her original mass within that compact form. Her surface temperature is searing, well over 100,000 degrees in the first stages, and she shines with a bluish-white light that is pure, unfiltered heat. But there are no longer any nuclear reactions at her heart. The light she gives off now is only the slow leaking of stored thermal energy, the gradual cooling of a furnace that will never burn again. The transition from red giant to white dwarf has stripped Aurelia of nearly all the grandeur she once possessed. She no longer has a vast crown of gas, no surging winds, no fusion-driven storms. Her planetary nebula, though still expanding around her, is already beginning to grow thin, its colors fading as its material disperses into interstellar space. And at the center of that fading shell sits Aurelia's remnant, silent, compact, and impossibly heavy for its size. A single teaspoon of her matter would weigh tons under Earth's gravity, for her atoms are crushed so tightly that their electrons are locked into place by quantum pressure. She no longer pulses with the rhythms of fusion. The internal heat slowly conducts outward, and the energy radiates into the cold dark of space. This process is unimaginably slow. Even as millennia pass, her surface will remain hotter than the surface of most stars. But without the replenishment of fuel, the decline is inevitable. In tens of billions of years, she will cool to a faint red glow, then to a dull orange, and finally to the darkness of a black dwarf. A hypothetical stage no star in the universe has yet reached, because the cosmos is not old enough. For now, she is a beacon of clarity and stillness. Aurelia's structure is stable in a way her earlier stages never were. There is no longer any risk of sudden collapse or explosive outburst. Electron degeneracy pressure supports her against gravity perfectly, a delicate quantum balance that can last for trillions of years, so long as no catastrophic collision interrupts it. She will simply sit in the void, cooling and fading, an eternal ember drifting among the stars. Her gravity remains strong, far stronger than her small size suggests. Any object wandering too close would feel its pull sharply, spiraling inward in a final plunge. If she were to capture a companion, perhaps a rogue planet or a passing brown dwarf, new activity could briefly flare as material fell onto her surface, releasing bursts of energy. But absent such events, her life is now one of solitude. The planets that may have survived her red giant phase are either far away or entirely gone. The system is empty except for dust and cold rock, and even those will slowly drift away under the influence of other passing stars. Around her, the galaxy continues its restless cycles. New stars are born from clouds like the one that once birthed Aurelia. Massive suns explode in supernovae. Spiral arms twist slowly in their stately rotation. She is no longer part of that drama in an active sense. She is a witness now, not a participant. But her witness role has its own quiet dignity. The atoms locked within her white dwarf body are relics of the very beginning of the universe, processed and reshaped in the crucible of her own life. The silence of a white dwarf is deceptive. While her outer appearance may be static, her interior remains a place of immense density and pressure. The carbon and oxygen that make up most of her mass are arranged in crystalline lattices, slowly solidifying as she cools. In the distant future, Aurelia will become, in effect, a vast diamond drifting through the galaxy. A gemstone forged not in minutes under earthly pressure, but over eons under the crushing weight of a collapsed star. Astronomers have already detected white dwarfs beginning this crystallization process, and in that sense, Aurelia's final transformation is not an end but a kind of frozen permanence. Her light, while diminished compared to her main sequence glory, still reaches out into space. Any civilization with sensitive enough instruments could detect her, measure her temperature, and deduce her age from the rate of her cooling. They would know she was once a star, and perhaps even reconstruct the details of her red giant and planetary nebula phases. In that way, she remains part of the galactic record, a silent entry in the story of stellar evolution. The timescale of her fading is incomprehensible to human minds. Civilizations could rise and fall a million times over before her glow dims by even a fraction. Continents could shift, galaxies could drift apart, cosmic structures themselves could begin to unravel under the acceleration of the universe's expansion, all while Aurelia quietly cools, unchanged to the eyes of anything watching over the brief span of a mortal lifetime. Her existence now is not measured in millennia or millions of years, but in billions and trillions. Eventually, far beyond any future we can imagine, she will radiate the last of her warmth into the universe. The background temperature of the cosmos will approach her own, and heat exchange will slow to nothing. At that point, she will have become a black dwarf, dark, invisible, and inert. No light, no heat, no activity will mark her presence, though her gravity will remain. But this final stage is so far in the future that it belongs to a universe utterly unlike the one we know now. A universe where even galaxies may have ceased to shine. Until then, Aurelia's white dwarf form will continue its vigil. She is the epitome of stellar endurance, stripped of all extravagance, yet enduring longer than any of her earlier selves could have dreamed. The quiet remnant at the heart of her planetary nebula is not just the end of a star's life. It is the beginning of a nearly eternal afterlife, one lived not in brilliance, but in stillness. She will not explode, she will not reignite, she will not return to her earlier youth, but she will remain, and in her persistence lies her final legacy. In the great arc of cosmic time, Aurelia has gone from a collapsing cloud to a blazing giant, from a queen crowned in red light to a ghostly ember. Now, she exists in a form that will outlast the Milky Way itself, watching silently as the universe continues its restless expansion. Her story has been one of transformation, each stage a chapter in a vast and ancient tale. But the chapter she lives now is the longest of all, a long, quiet epilogue written in white fire that slowly dims into the infinite night. Long after Aurelia's red giant crown has faded and her planetary nebula has dissolved into the interstellar medium, the gas and dust she cast into the galaxy continue their journey. These fragments of her body, hydrogen, helium, carbon, oxygen, nitrogen, silicon, and more, are no longer part of a star's coherent form. They drift through the void as scattered atoms, grains of dust, and invisible clouds, each particle tracing its own slow orbit around the galactic center. But though they are dispersed and quiet now, they are far from inert. In time, the galaxy will call them into new service. The material Aurelia shed is not ordinary in the cosmic sense. It is enriched. When she was born, the galaxy contained mostly hydrogen and helium, the primordial elements forged in the first minutes after the Big Bang. Heavy elements like carbon, oxygen, magnesium, and iron did not exist in any meaningful quantity until stars like Aurelia forged them in their cores. Every carbon atom in the breath of a future living creature, every oxygen atom in an alien sea, every grain of silicate dust in a rocky planet's crust. These all come from the interiors of ancient stars. Aurelia's winds and her glowing nebula carried such atoms out into space, scattering them into the galactic ocean where they could one day be recycled. For a while, her material will wander aimlessly. Some of it will cool and join vast, diffuse clouds spanning dozens of light years, faint wisps of hydrogen threaded with dust. Some will be swept along by supernova shock waves from other, more massive stars, compressed and accelerated in a chaotic dance of turbulence. Some grains will drift for millions of years without significant change, dark specks in the cold vacuum, absorbing faint starlight and re-radiating it as a whisper of heat. But the galaxy is not a static place. Gravity is always at work, and over the course of tens or hundreds of millions of years, the enriched gas will find itself caught in the slow but inexorable collapse of a molecular cloud. This is where Aurelia's atoms will truly begin their next chapter. Shockwaves, perhaps from the death of other stars, will ripple through the cloud, causing denser pockets to form. As the pressure in these pockets rises, gravity will take hold, pulling the gas inward, heating it, and eventually sparking the birth of new stars. When that happens, Aurelia's legacy will become woven into the fabric of these new suns. Some of her atoms will be trapped in the fierce heat and pressure of stellar cores, beginning the cycle of fusion anew. Others will orbit farther out, remaining in the cooler, flattened disks of dust and gas that form around newborn stars. In these disks, the dust grains will collide and stick together, forming larger and larger clumps. Over time, these clumps will grow into planetesimals, and then into fully formed planets, moons, and asteroids. The planets born of Aurelia's dust will be richer and more diverse than any that could have formed in the early, metal-poor universe. Carbon-based molecules will exist in abundance, enabling complex chemistry. Silicate rocks will form strong crusts and mountains. Iron will sink to planetary cores, generating magnetic fields. If conditions align, right distance from their star, the presence of water, a stable atmosphere, these worlds could even host life. On one of them, perhaps billions of years from now, a sentient being might look up at its sky and wonder where the atoms in its body came from. Without knowing it, it might be carrying within its blood the oxygen forged in Aurelia's heart, or the calcium from her dying breaths. It is this recycling of stellar material that makes the universe fertile. Without it, there would be no rocky planets, no oceans, no biology. The galaxy itself is like an immense organism, with stars as both creators and destroyers, each generation passing on the elements needed for complexity to the next. Aurelia's life was part of this cycle. She was not born with the atoms she gave away. She inherited them from even older stars, perhaps from supernovae that exploded billions of years before she ever existed. Now, she has added her own contributions to the mix, sending them forward into the galaxy's future. Even as Aurelia's white dwarf cools in solitude, her atoms will be on the move, participating in events she will never witness. Some may travel beyond the Milky Way entirely, ejected by gravitational interactions into the intergalactic medium. They might drift for eons before encountering another galaxy and joining its own star-forming regions. Others may become part of comets in new solar systems, icy time capsules carrying organic molecules to barren worlds, sparking chemistry that could lead to life. In a sense, stars like Aurelia are the universe's memory banks. They store, transform, and distribute the elements that shape everything else. The matter she has released will carry her story, not in words, but in atomic fingerprints, ratios of isotopes, traces of rare elements, that future astronomers, perhaps alien ones, could identify. They could trace a certain grain of dust to a planetary nebula that once shone in a distant arm of the galaxy, and realize that this grain came from a specific type of star, one that lived briefly but brightly before yielding its treasures to the cosmos. It is a humbling truth that much of the matter we take for granted on Earth, our bones, our blood, the soil beneath our feet, was forged in stars and then scattered into space by processes much like Aurelia's gentle farewell. Without such events, the universe would still be in its infancy, chemically speaking. The fact that humans can stand on a rocky planet, breathe oxygen, drink water, and gaze at the stars is the direct result of countless stellar lives and deaths. Aurelia's contribution may be just one among trillions, but it is essential all the same. Her stardust will not immediately assemble into something new. The galaxy moves at its own pace, and the process of forming stars and planets from diffuse gas can take hundreds of millions of years. But time is abundant, and the materials she left behind are patient. When the right conditions arise, when gravity gathers them into a dense knot within a cold molecular cloud, her atoms will again be drawn toward the heat of creation. Another sun will blaze into life, and around it, new worlds will coalesce. Perhaps, on one of those worlds, eyes will open for the first time and see the light of their star, unaware that part of that star's substance once lived and shone far away, as Aurelia. In this way, stars never truly vanish. They disperse, transform, and return. Aurelia's light will one day fade entirely, but her presence will persist in the stones of new planets, in the air of alien skies, and in the beating hearts of living things. The atoms she set free are her legacy, scattered like seeds across the galaxy. Some will remain adrift forever, but others will take root in the fertile ground of new worlds, ensuring that her story, written in the very substance of the universe, continues long after her final light has gone. In the silence of the cosmos, Aurelia's white dwarf cools in isolation, her once blazing light now a pale ember among countless stars. The glow that once warmed worlds, that once illuminated her planetary nebula in shimmering hues, fades with each passing million years. Yet this is not an ending in the human sense. In the great ledger of the universe, nothing is struck out and erased, only transformed, passed along, woven into new patterns. Aurelia's story has reached its quiet chapter, but the cycle she was part of continues without pause, carrying the memory of her existence forward in ways more profound than light alone could achieve. The universe does not waste. Every photon Aurelia emitted during her main sequence years has traveled outward, never to return, but never lost. Those photons still wander through space, some passing unnoticed through the void, others striking dust particles, heating them faintly, others perhaps falling on the surface of a distant world and adding the tiniest fraction of warmth to a sunset sky. Her stardust, enriched with the elements she forged in her core, now drifts within the galactic medium, waiting for gravity's inevitable call. Whether it takes 10 million years or a billion, those atoms will be gathered into something new, another star, another planet, another chance at life. The cycle that sustained Aurelia is as old as the galaxy itself. Clouds of hydrogen collapse under their own gravity, giving birth to stars. Stars live out their luminous years, fusing elements in their cores, transforming simple atoms into complex ones. Then, through death, gentle or violent, they return their enriched matter to the interstellar medium. That matter becomes part of the raw material for the next generation of stars. Each iteration deepens the universe's chemical richness, allowing for more intricate planets and, potentially, more complex life forms. Aurelia was one link in this chain, inheriting the ashes of older stars and bequeathing her own to the stars yet to come. From the perspective of a galaxy, this is a perpetual dance. At any given moment, countless stars are being born, countless others are dying, and the rest are somewhere in between, each moving according to the simple but unbreakable rules of physics. And yet, in the patterns of light and shadow, in the way matter and energy flow between forms, there is an almost organic elegance. It is not life as we define it, but it is something akin to breathing. The inhale of creation, the exhale of dispersal, repeated endlessly. For Aurelia, the dance goes on without her conscious presence. The gas she expelled will spiral into new clouds. Some of those clouds will be stirred by the shock waves of nearby supernovae, compressed into knots of star-forming material. Her carbon may find itself in the atmosphere of a terrestrial planet orbiting a young star. Her oxygen might dissolve into a sea under an alien sky. Her calcium might build the bones of a creature that evolves to walk upright, to think, to look into the night and wonder about the origins of its world. The same process will shape and reshape countless other stars. Aurelia's siblings, those that formed beside her in the same nebula, have long since taken their own paths through the cycle. Some may already have ended in spectacular supernovae, scattering heavier elements like iron and gold into the galactic currents. Others, less massive, may still be quietly burning hydrogen, their fates yet far in the future. The galaxy holds billions of such narratives, overlapping and interwoven, all contributing to the grand tapestry of stellar evolution. On the smallest scale, this cycle is about atoms. A single carbon atom forged in Aurelia's core might spend millions of years floating in the vacuum, then become part of a grain of dust in a new star system, then be incorporated into the bark of a tree on an alien world, then be released again into the atmosphere when that tree burns, then drift into another life form entirely. The journey of matter is never linear, never final. There is only transition. On the largest scale, the cycle shapes galaxies. The bright spiral arms of the Milky Way exist because of continuous star formation, which in turn depends on the enrichment of the interstellar medium by previous generations of stars. If stars like Aurelia had never died, returning their processed matter to space, the galaxy would be chemically barren, unable to produce rocky planets, oceans, atmospheres, or life. Death is not an interruption of the cosmic order. It is a necessary part of its progression. Even the end of the cycle is not truly an end. Far into the future, when the galaxy has used up most of its gas for star formation, when the last red dwarfs flicker out and black dwarfs replace white dwarfs like Aurelia's remnant, the matter will still exist. It may no longer form new stars, but it will remain in some form, perhaps as cold dust drifting between the remnants of galaxies, perhaps as material pulled into the gravity wells of black holes. The universe's energy will thin out, but the atoms will persist. This endurance is the quiet truth beneath the apparent finality of death. For humans, endings are tied to consciousness, to the cessation of thought and sensation. For stars, there is no such boundary. There is only transformation and redistribution. Aurelia is no longer a source of light and heat, but she is still here, in the dust clouds illuminated by other stars, in the gravitational eddies of the Milky Way, in the unseen building blocks of worlds yet unformed. And so the cosmic dance continues, with each generation stepping into the place of the last. From the faintest brown dwarfs to the most massive blue supergiants, all stars play their part. Their lives may be brief or enduring, quiet or explosive, but each leaves behind something essential for those that follow. Aurelia's own contribution is now diffused into the galaxy, invisible to any casual observer, yet it will resonate through time in the structure and chemistry of things that do not yet exist. If there is a kind of immortality in the universe, it is this. The atoms that once formed the heart of a star will always be part of something. They may change form endlessly. They may travel farther than any mind can imagine, but they will never cease to be. Aurelia's light may one day be forgotten, but her substance will remain, playing its part in shaping the next chapters of the cosmos. The endless cycle is not a closed loop. It is a spiral, each turn building on the last, creating greater complexity, richer chemistry, and new possibilities. It stretches backward in time to the first stars that ever burned, and forward to whatever distant future the universe will allow. In this vast and unbroken sequence, Aurelia's life and death are a single brushstroke on an infinite canvas, yet without it, the picture would be incomplete. And so, somewhere in the galaxy, the seeds she scattered are already moving toward their next destination. The dance continues, the cycle endures, and in the life of the universe, nothing is ever truly lost. Good night.